Okay, so let's look at an induction motor problem, and I'm actually going to do this differently, different numbers. I'm going to put in different numbers here, and I'm going to say let's look at a situation where we have rated slip. I'm going to give you the slip is 0.03. I'm going to give it to you in 2%. 3.2% rated slip. So that's the same as saying S equals 0.032. And I want to ask you what is. I'm going to give you the parameters R1, X1, X2, XM. We're going to say that RC is almost infinite, so we'll ignore that, and R2. And I've got what I'm going to give you is R1 is 0.17 ohms, X1 is 1.05, X2 0.87, R2. Just bear with me. I want to go through this another 5 minutes. R2 is 0.24 ohms. This was 0.87. And then XM, which is 82 ohms. This little example problem here, this is too, I think that's a mistake too. It's too close to the other values. But anyways, these are the parameters I'm going to give you. And if I want to find the rated torque, the easiest way for me to solve this problem is to use the first equivalent circuit that I gave you, which is this one. We don't have the RC in there. This is the rotor current I2. I've got a V1 applied right here. So how do I go about solving this problem? Well, I have to use phasor math, obviously. We'll have to give you the rated voltage. I'm going to give you, it's always given to you in line to line. So it's 400, I was just double checking my numbers. It's 460 volts RMS, line to line. And it's 60 hertz is the frequency. So if I want to go about solving this problem, I have to find V1. So what is V1? Well, this is kind of my reference point. It's a line to neutral circuit. Remember, you have to convert to line to neutral. Divide by square root of 3. I'm at a 0 angle. And so I get that is 265 0 degrees volts. That's V1. Now, what I have to do to find the torque is I have to find this current. So I'm going to have to first find this current, and then I'm going to have to do a current division. So what I'll do is I'll say, let's take, there's this impedance right here. It's in parallel with this guy here. So I could call this the Z2, the rotor impedance. if I look in here, I could call this, it's basically Z2 in parallel with JXM. And then I've got to add the stator impedance to it. So basically, I've got to find a Z in, which is Z1 plus JXM Z2 over Z2 plus JXM. So I got to find that impedance there. And then I1 would be equal to V1 divided by Z in. Now that I have that, I need to find I2. I have to do a current divider. So I2 would be I1 times JXM over Z2 plus JXM. Now I've got that. Then I can find the rated torque. It'll be helpful for me to find, I could just say that P gap is equal to 3 times R2 magnitude of I2 divided by S. And I might as well just, I could find the losses in the rotor, which is 3 times, well, oh no, see, I'm messing, I could do it even better. Once I know that, I know P mechanical is 1, since I know slip. If I didn't know slip, I'd do it differently, but I know slip. That's 1 minus S times PG. And then the T mechanical rated would be the P mechanical divided by the mechanical speed. So that's simple, okay? Those are the steps, the minimum steps to get there. So, you know, I actually pre-calculated these, but I found Z in, and that was equal to 7. Oh, let me do one step here first. The first thing you do is you need to find R2 over S. This is the biggest mistake that's made in exams. They forget this. So I know S is 0.032 and I know R2. So it's 0.24 divided by 0.032 because this is going to change with load. So if I take 0.24 divided by 0.032, that's 7.5 ohms. That's essentially the load resistance. This is what I called my rated slip. And so the Z in under rated conditions ends up being 7.9 ohms, and then the angle of that impedance is 19 degrees. Now I could find to find the output torque, I only care about the magnitude, but I could also find the input power factor if I want. So the whole phasor current, I1, is V1 divided by Z in. So that's 265 divided by 7.9, 0 degrees, 19 degrees here. So that's 265 divided by 7.9, which is 33.5 amps. Negative 19 degrees. I know my power factor So there's my line current. My power factor is cosine of 19 degrees. Which is 0.95. Looking into this motor, I could find my rated volt amperes. That's going to be square root of 3, 460, 33.5. Now, I mean, I'm going to just finish this. I know I went over, but I think it might be helpful for you all to see this. That's 27 kVA. So let's go back. Let's go find the. You guys want me to keep going, or do you want me to stop? Because we're 5 minutes over.
You can finish.
Okay. Well, let's find the we did this. We did this. So we're going to find the rotor current. And I don't really care, well, I don't think I care about the angle of it, but we'll put the whole thing in there. I1 times this, I've got to do this current division here. I didn't pre-calculate this. GXM. I did this really fast, so we'll see if everything works out. Makes sense here. So that's 33.5 negative 19 degrees times the XM, which was 82. J, that's a 90, right? Now I have to divide by Z2 JXM. Now I pre-calculated Z2, and my Z2 was 7 point, it was this, 7.5 plus J 0.87 plus J 82. This is the Z2. Well, I know what that is. That's R. That's, I found that R2 over S here, right? 0.87 is the leakage inductance of the rotor. So I just convert this to a magnitude now. So I'm squaring the 7.5 and squaring the sum 87.82, and that's 88. So this ends up being 33.5 times 82 over 88. I don't really care about all the angles because I'm just after the amplitude. So it's 33.5 times 82 over 88. Now that makes a lot of sense. The rotor current's going to be some reduction because there's magnetizing current that went down the branch here, right? So a little bit of it goes there and the rest goes over there. But it's not negligible what goes down the magnetizing branch. So 33.5 times 82 over 88 is 31.2 amps. So I could find the P gap 3 times 31.2 squared times the rotor resist times R over S, which was 7.5. So 31.2 squared times 7.5 times 3 is 21.9 kilowatts. That's the gap power. Now notice that I've got here, remember I found the volt amp. Let's check this. So that's my input volt amperes, 27, and my gap power is 22. I know the input power factor, so I could find the input power from the stator side. That would be 0.95 times 27 kVA, which is 25.7 kilowatts. So I'm dissipating about 5 kilowatts in the stator. It's about the difference between PG and PN. You know, I could know exactly what my stator losses are now from this if I wanted. You know, it's essentially P stator I squared R, which is 3 times RS magnitude of I1 squared, but I don't even have to do that because it's going to be PN minus PG. Now, the rotor I squared R loss little r here is going to be 3 times 31.2 squared times the rotor resistance, which was 0.24. Oh, yeah, remember I said I don't even have to do this. This is too much work. I just wasted time. Okay, and I want to get my exam done. So I know the slip, right? So P mechanical, I could have found this and subtracted it from the P gap, but I could just say T mechanical is equal to 1 minus the slip times PG. 1 minus 0.024 times 21.9 kilowatt, and that is, so 21.4 kilowatt. The way this thing's working out, I don't have, yeah, it's a little bit weird, but I mean, I'm showing you the process. I think the losses seem a bit low compared to what I had in the stator. I have to go back and look at that. I'll probably clean these notes up and make sure we got everything. I didn't miss a decimal point or something. But this is close. That's the mechanical power. So essentially the efficiency from input to output, we can check that. It's going to be 21.4 kilowatts divided by my input power, which was 25.7. So 21.4 divided by 25.7, it's 83%. That seems a little bit low. So I'm going to redo it, but I'm going to stay tuned. But the next thing I want to do is I'm going to check this. I'll clean this up. T mechanical is the mechanical power divided by the mechanical speed. So all I need to know is the mechanical speed. Well, what is the speed of the rotor? N. It's going to be 1 minus the slip times the synchronous speed. Now, one thing I didn't tell you, which I should have, was I had to tell you how many poles there were. So let's say it's a 4-pole machine. So, because I have to know that, and that means I know that this is 1800, 1 minus 0.0. You know what I think I did? I was changing my slip number. I know what I screwed up. It's not 0.024. It's 0.032. You see, I put 0.024 because it was going so fast. This is wrong. 0.032. 1 minus 0.032 times 21.9. That's a lot better. $21.2. My P-gap was, it's still a little bit weird, only 0.7 kilowatts. It's like the stator losses were so high. So I got to go back and double check something. But anyway, 21. So it's not going to change this number. This seems a little low, and I think that I might have made a mistake somewhere.
Yeah, your mistake is the fact that when you converted the slip speed, you put 32% is not 0.032, it's 0.32. Because what you have is technically 3.2%.
32% is, it's 3.2%. It's not 32%. It's 3.2. It's not 32. I may have said that, but it's 3.2. 0.032 is the right number.
Oh.
So anyway, bottom line, there might be some small error. I'm going to go find it. But 0.032 times 1800 gives me my speed. 1 minus 0.032 times 1800. That's 1742. I think one of the big issues is that the slip that I assumed is a little bit, it should be higher than 0.032. That was just kind of an arbitrary number. I think that's the issue. I don't think I did anything wrong. It was just the number that I picked for slip is a little bit low. Okay, so this is the RPM. Now I can convert this to mechanical speed. It's going to be 1742 times pi over 30. So 1742 times pi over 30, which is 182.4 radian per second. And so my rated torque is my mechanical power, 21.2 divided by 182.4. And there it is right there. So that's 21.2, 182.4, 116 Newton meters. And there it is. Now the one other thing, I could put my P mechanical in horsepower. That's probably the way things are looked at from the motor standpoint, because we have to remember that horses used to do everything. Okay, so we got P mechanical, 21.2 kilowatt. I'm going to divide it by 746, just to give me an idea of the horsepower rating of the motor. So if I had to buy it in the 1970s, definitely it would give me this. Now, the rusty nameplate would have that possibly. Today, they use kilowatts more often, especially if you're buying things anywhere outside of the United States. So that's a 28 horsepower motor. I want to pick back up on the example of the induction motor equivalent circuit, and I also want to introduce two additional equivalent circuits. So first of all, let's just talk about the equivalent circuit and how we solve problems with it. So we're talking about the induction motor. We had derived an equivalent circuit that looks like this. This is your input voltage, V1, on the stator of the induction motor. This would be I1, the current of the stator, R1, stator resistance, JXL1, the stator leakage reactance, JXM, the reactance of the magnet, basically the magnetizing reactance. You've got the air gap voltage that gets applied to the rotor here. The leakage inductance on the rotor at JXL2. And then we represent the load resistance as a load resistance R2 divided by the slip. So just to review, with the induction motor, it's an asynchronous motor. It's an asynchronous machine. What that means is that there's a stator MMF that is developed associated with that stator. It's traveling at the synchronous speed just as it did with the synchronous machine. But there is a MMF and associated flux that's induced into the rotor. And that MMF or flux of the rotor travels at a speed of what we would call a slip speed, which is S times synchronous speed. The result of this is that the rotor itself will not travel at the synchronous speed, but the rotor speed is going to travel at a speed that is the difference between these two speeds. The synchronous speed minus the slip speed, or 1 minus S times the synchronous speed. We have defined so far the synchronous speed as a mechanical speed, which means that it's related to the electrical frequency applied to the stator by the inverse of the poles. Where omega E equals 2 pi times Fe. So this is the frequency of the stator currents. We could say, well, what is the frequency of the rotor currents? That's a good question. We actually can find it from the slip frequency. So a similar relationship will result with the rotor, where we have slip times the synchronous speed is equal to 2 over poles times the electrical frequency of the rotor, where omega ER equals 2 pi times the rotor electrical frequency. So what we mean by this is, let's just say we have a 4-pole motor. The electrical frequency of the stator is, I'm going to use 50 hertz because we're always, using the same numbers. Let's just mix it up a little bit. I'm going to do another pole motor too, just to mix it up even further for another example. So the slip can be found, let's assume that we have a rotor speed and we want to find out what that is. Well, let's find the synchronous speed first, and then we can deduce from that what the rotor speed might be or what range the rotor speed might be in. So the synchronous speed, omega s, is going to be 2 over poles times 2 pi times 50. So that's 2 over 4, 2 pi times 50, which is equal to 157 radians per second. I'm going to convert this into a RPM. So this would be the synchronous speed in RPM would be 157 radians per second multiplied times the ratio of 30 over pi to put it in there, those terms. And so that means it's 1500. So what this tells me is that the rotor speed N is going to be less than 1500 because we know that the rotor speed is 1 minus S times the synchronous speed. It's not going to be greater than 1500, and it's not going to be significantly lower than 1500. The important point here is that the slip is going to be less than or equal to 1. And we can think about, what does it mean if the slip is 1? What if S equals 1? Well, the speed would be 1 minus 1 times the synchronous speed, and it would be 0. So this is startup of the motor, or stall. You've locked the rotor so it can't move. That's a slip of 1. That's a pretty extreme slip condition, the most extreme that you could have. Typically, the motor's going to operate with a slip in the range of, let's say, between 0.01 to 0.1. 0.1 being a pretty extreme operational slip. So the rotor speed isn't going to be significantly lower than the synchronous speed, but this is always the case. The rotor speed will never be equal to the synchronous speed. So you could say at no load, S is equal to 0.01. This is a motor with a very high, relatively, I'm going to show that the slip at full load would be higher than normal. So probably what, not even your typical motor. Then what the the rotor speed would be 1 minus 0.01 times 1500, or 0.99 times 1500. So it's close, but it's not exactly equal to the slip. So that's at 1485 RPM. Let's say at full load, slip is 0.08. Then the N would be 1 minus 0.08 times 1500. So that's 1380 RPM. That's a pretty extreme range, but it is possible. So if I say you may be asking yourself this question about slip, and well, how do I know what a slip is of a motor? Well, typically motors have nameplates, and we talked about this before. What that meant was, actually, I haven't looked at recently built motors, but spent a lot of my teenage life following my father around. He was an HVAC mechanic. I had to carry his tools for him and trying to work on compressors and pumps and things like that. There was always motors, and we always had to look at these motors. They were full of dust and dirt, and you'd go look at the motor. If you had to replace it, you'd have to clean it off and find the nameplate. So there'd be this little thing sitting there, and hopefully it was readable, and that would tell you, the make, model, and nameplate information of the motor. So typically, what is the nameplate going to tell you? It's going to tell you the speed. So the rated speed it probably just lists the values. It doesn't give the symbols, but I'm just giving you the symbols. So maybe I've got a speed of, I'm in Europe, so this is a typically European motor running at 50 hertz instead of a US motor. I've got, let's say, a rated speed, so that would be the speed that would be on the motor, of 14, let's say 70. That's probably a better number than what I've just put here. I've got the frequency is listed, would be 60 hertz, or sorry, 50 hertz. I've got the line voltage will be listed, probably, let's say 400 volts, and I've got the power rating, so that might be given in horsepower or kilowatts. If it's in Europe, probably in kilowatts, so we could say, oh, maybe it's a 15 kilowatt, and that would be the P rated. Or it might give me also the line current and roughly what I would expect. I could say, let's take a guess on what this might be. If this was this is information that's not on the nameplate, it might be, but power factor and the efficiency. So if I knew those things, I could find the line current, or the line current might be given, and then I would be able to know what these were. So let's assume a power factor of 0.82, an efficiency of 0.85. Typical induction motor power factor and efficiency. And so the line current is going to be equal to the line-to-line voltage. I'm sorry. The line current is going to be equal to the rated power. This is the rated line current divided by square root of 3 divided by the line-to-line voltage. And then to get to the we're going to assume that this power here is the shaft power. So that's the load that's on this thing that it can handle, but there's probably some efficiency. Since I've given you this efficiency here, I've given you this efficiency here. It could be applying from the P P shaft to PN, or it could be applying from the P mechanical to PN, one of the two. I always assume it's P shaft because it gives me a little bit of conservativeness, but a lot of times it's really just the P mechanical. So you'd have to take whatever this power is here divided by that efficiency, and then to get to the volt amperes, the S, you'd have to divide it by the power factor. So that would be the input volt amperes right there. So that's 15 e to the 3 root 3 400 0.82 0.85, and we're going to get a 15,000 divided by root 3 divided by 400 divided by 0.82 divided by 0.85. I'm getting 31 amps. So there'd be maybe a rated ampere there as well. So there's a typical machine. What would be the frequency of the currents in the rotor? Now these will change depending on load. So we're going to say under rated load. So we have to find the slip. The slip is going to be equal to the synchronous frequency minus the actual synchronous speed minus the actual speed divided by synchronous speed. The synchronous speed for this, the other thing, this machine will also give the number of poles. So we'll say it's a four-pole machine. So we've already found out what the synchronous speed of the four-pole machine is. We look up here, it was right here. Yes. 1500. So 1500 minus the rated speed, which is 1470, divided by 1500, and I have a slip now. I'm sorry, let me do that again. 1500 minus 1470 is 30 divided by 1500. So 30 divided by 1500 is 0.02. That's the slip. So the rotor frequency, FER, is going to be equal to poles divided by 2 times the slip frequency, so that, or the slip speed. So that's S omega S, and this is in radians per second, divided by 2 pi, because we want to get a frequency. So 4 over 2 S times, so the S is 0.02. The omega S we found up here, 157. And divided that by 2 pi. Okay, so that's 0.02 times 157 divided by 2 pi. .02 times 157 divided by 2 divided by pi multiplied times 2, and that's about 1 hertz. So let's double check that. So 2 times, that's what this is, 0.02 times 157 is 3.14 divided by 2 pi. Yeah, it's going to be about 1. So basically this is pi. 2, that's pi, that's 2, and that's pi. It's exactly 1 hertz pretty much. So that's pretty interesting. So you have a very, very low frequency in the rotor. But that's the electrical rotor. So if you were to look at, if you could actually monitor the current in the stator and the rotor, we're saying that you're going to have a stator, currents are going to look like this, and your rotor currents are going to look like, you know, really low frequency. This is exactly the way it's going to look. So this is a little tricky thing that's important to understand how motors work. So going back to this motor problem, how do we solve motor problems? So let's say we're given the motor parameters, and we're given speed or slip, and of course the operational variables like the voltage, line-to-line voltage applied to the stator, and the frequency. So this is basically what I call a left-to-right problem. Your typical circuit problem. What you've got is you've got a voltage that's applied right here. This is going to be the line-to-line voltage divided by √3, because you've got to convert it to a per phase at 0-degree reference. Fill in your parameter values for everything. Actually, I've got to put these values and be consistent here. XL2, XL1, R1, R2, I1, I2. So we're asked for find the motor torque. Let's say that we need to find what that is. We want to find what the find the line current, the input line current, and power factor. So the way you'd go about solving this is just to review what we showed in the last lecture, is that the first thing you would do is you would find I1 by looking at the circuit terminal properties. So we essentially take this whole circuit right here and we'd reduce this down into an input impedance, and we would say that I1 is equal to, this is V1 here, V1 divided by Zn. So you have to find Zn. To do that, you've got to take these two impedances and put them in parallel with this, and then add this in series. That's the example we went through in class last time. And then when you do this division, you're going to have I1 is equal to the V1 has got a 0 degree reference, so there's just a voltage on the top. So you could say the line to neutral RMS voltage divided by Zn, that's V line to neutral. You've got an amplitude of Zn, and you've got an angle of the impedance. This goes back to the very first week of class. It's going to be V line to neutral Zn minus the impedance, input impedance, and remember that the power factor angle is equal to the negative phi z. So this is the power factor right here. So you've actually had to find these things first in order to solve this problem. Once you know this current, you need to find I2 to find the torque. So to do that, you can do a current division, a current divider. So you know I1 already, and it's going to divide up between the branches of the magnetizing reactance and this rotor impedance here. So you're after I2 right here. So the I2 would be equal to the I1 do a current divider. And there's your I2. And so the torque, we're going to focus in on this. What's the torque? Okay, so this is the power. There's a power that is dissipated across this resistor right here. And that power is going to be equal to the magnitude of the I2 squared times R2 over S. And for the motor, you're going to have 3 times this. So what is this power? This power is called the gap power. Take 3 times whatever we have there, I2 squared R2 over S. That's our gap power. Now how do we get the torque? Well, here we introduce the second equivalent circuit. Part of this power here is losses of the rotor resistance and the other part of this power is the mechanical power that gets applied to the shaft. So we could actually break this up if we want. And we know that the rotor resistance loss, the P loss, I squared R of the rotor is going to be equal to, for one phase, the magnitude squared of I2 times R2. So we could easily break this up and we can come up with a new equivalent circuit. That equivalent circuit is going to look like this. Stator looks the same. Magnetizing inductance. The rotor leakage. Now I'm going to split out the losses. So this is the winding losses of the stator. This is the rotor loss. And then what's left here is associated with the power that's applied to the shaft. This becomes R2. 1 minus S over S. It's just manipulating everything to get it into this form. And so from this, I could directly, and also want to point out that this is a variable resistor because S is variable. So in the book, they show it like this. It's kind of like this silly thing here, like it's a rheostat or something like that. There's your losses there, and then the rest of the circuit. So the P mechanical is equal for the whole motor 3 times, because you have 3 phases, magnitude of I2 squared R2 1 minus S over S. So that's the mechanical power. You can find that if you know I2. Now, how do you get torque? Well, in the mechanical world, they don't use volts times amps to find power. They use torque times speed, where that's the mechanical speed. So if you rearrange this, the electrical torque applied to the shaft, or you could call this T mechanical, but this is the common term that we've been using for the other motors. T subscript E, that's going to be P mechanical divided by the mechanical speed. So let's plug that in and find an expression for torque. So I'm just going to keep this symbolic right now. And let's say, what is the mechanical speed? So the mechanical speed, and I'd like to write this in terms of, I know this speed already for this example, so I can just plug it in. But to write it symbolically, remember that the mechanical speed is equal to 1 minus the slip times the synchronous speed, omega s. It's also the same as to say 1 minus s times the electrical frequency times 2 over poles. So the expression then becomes P mechanical divided by times the number of poles divided by 2 times the electrical frequency times 1 minus s. So let's plug this in to that. We have 3 times I2 magnitude squared R2 1 minus s over 1 minus s, which this is going to cancel, s 2 omega e, or 3/2 I2 squared R2 s omega e. So there is our electrical torque expression if we know the rotor current. So this is really taking you through how you would solve it, the steps, starting out with this motor circuit, assuming you were given all of these parameters right here. Yes. Okay, so to summarize what we have now are 2 equivalent circuits so far. I'm going to write them kind of the way they are in the textbook. We've got the circuit that's probably the easiest to use if we're solving a left to right problem. It's really lumped parameters per phase equivalent circuit. And then the second circuit that we just derived. I'm going to write all these in here. Was very similar. We just broke out the rotor losses. I said I was going to write it the way it's done in the book. So this silly little rheostat looking thing here, showing you that you have a variable resistor. And then we show the losses broken out. And we can come up with a direct expression for the mechanical power applied to the shaft and the torque by looking at this resistor here. Okay, so that's circuits number 1 and circuit number 2. It would be really nice if we could derive everything from the terminals and not have to go through all this math to do it every time. So what we could do is we could apply Thevenin's theorem and come up with an equivalent circuit that really what we're interested in always is what's happening on the rotor side. So I could take either one of these two circuits here. I'll just take the one on the left, R2 over S. And actually, I'm going to do the one on the right. R2, 1 minus S over S. And I'm really interested in what's happening right here. So I could take, I know that I've got these impedances here in the rotor. They're all in series. That's easy enough. But it'd be nice if I could get rid of this thing right here. Can I get rid of that? So I can do that by creating a Thevenin equivalent circuit where I have a Thevenin equivalent reactance for the stator impedance called JXL1 equivalent. And then I have an R1 equivalent. And I would also have to have a equivalent voltage. So these are the kind of a Thevenin. This will be a Z equivalent. And there's going to be a V1 equivalent here. So I've really converted the left-hand side of the equation to an equivalent circuit. So this is the third form of circuit. And I'm not going to go through the steps of doing Thevenin equivalent, but just give you the formulas. But essentially, what have we really done? We've just said, let's take these things here, these impedances right here, I'm going to short this voltage out and find the Z1 equivalent, and then we're going to apply voltage division, putting this back in, and find a V1 equivalent. And so this is the circuit, quite simple, but just to remember what these formulas are things that you would want to write down in your notes for a test, for example, and be able to use them. In the next class, I'm going to show you how to use this and example of the best use of all three of these equivalent circuits. So V1 equivalent is JXM over R1 plus JX1 plus XL1. Just recognize I've been using L1 and the book uses X1. So this is X1. I'm teaching a drives class at the same time and I don't use those symbols. So it's a leakage inductance. Just don't get thrown off by, just look at the circuit. Okay, so that's that. The R1 equivalent is going to be the real component of a equivalent impedance that I would derive by shorting this out and looking at the parallel combination. And then X1 equivalent here is the real part of Z1 equivalent. And so then all you need to know is what is Z1 equivalent, and that is equal to JXM. It's basically just the parallel combination of the branches, R1 plus J, so 1 over R1 plus J XL1 plus XM. So we have this and this, and now we've got our equivalent circuit that we can solve problems with. And what's nice about this is we can find this is the current I2 directly, and it's going to be possible to simply say I know now that my I2 is equal to this V1 equivalent divided by Z1 equivalent plus JX2 plus R2 over S. Okay, so from this, finally, and now go into the details more next lecture, we can find a single torque expression using really in terms of the terminal properties. And that torque expression ends up being this 1 over the synchronous speed times 3 times V1 equivalent magnitude squared divided by R2 over S over R1 equivalent plus R2 over S, these are squared, plus X1 equivalent plus L2 squared. So we now have a new torque expression, and this is the expression that we can use to generate speed torque curves from. So next time I'm going to demonstrate that, and really handy often to just program this into use a MATLAB script, and we'll talk about the speed torque characteristics finally in the end.